All right, we're gonna deal with the compounds that have heteroatoms. Start with the nitrogen one. Okay, we got pyridine and pyrrole. Are these two compounds aromatic? They are, but with different reasons. Okay, we're gonna start with the pyridine. All right, I'm sure you guys know the pyridine, the nitrogen. This nitrogen has one lone pair. Okay, but here's how it works. This guy is aromatic. This nitrogen, what if this guy were to be aromatic? Right now we have how many pi electrons? 1, 2, 3, 4, 5. You gotta have 6 to be aromatic compound, right? The nitrogen is an sp2 nitrogen, which means that it got that p orbital and a 1 electron, right? So right now we have 6 pi electrons, so aromatic. The lone pair of the nitrogen does not occupy this p orbital. Instead, it's on an sp2 orbital, sp2, 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 and that's a p orbital. Okay, so the lone pair, basically this orbital is perpendicular 90 degrees against the p orbital in the ring. This lone pair is free, has nothing to do with aromaticity of this the pyridine. Basically, this lone pair will function as the base lone pair. If you add an acid, nitrogen can take that lone pair and abstract the proton. Okay, that's why you have seen pyridine in the reaction, like in the previous or the previous chapters, add a tosyl chloride, add pyridine. Okay, or in alcohol chapter, thionyl chloride and pyridine. Pyridine will come back. You will see pyridine later. Okay. All right. Just to remind, just review real quick. So the tosyl chloride looks like this. All right. You can convert alcohol to a better leaving group. So add tosyl chloride. You get a look like a hydronium ion. Pyridine will go abstract the proton. Okay. So you get the neutral, the product. Okay. So pyridine is an aromatic compound. Okay. The nitrogen have 1 electron in the p orbital. Now, pyrrole is also an aromatic compound, but with different reason. This nitrogen is actually an sp2, got a lone pair, and this lone pair actually participate in the ring, in the conjugation in the ring. Without the lone pair, if you minus the lone pair, how many pi electrons are there? 1, 2, 3, 4. Okay, and that's an anti-aromatic. All right, but once you add 2 lone pairs onto it, 1, 2, 3, 4, 5, and 6. Finally, we got 6 pi electrons, and this guy become aromatic. Okay, so basically this lone pair is being delocalized in the ring. This guy is not free, like in the case of pyridine. It's not a free lone pair. Okay, so it does not do remove it. This guy become non-aromatic. All right, that's the reason why pyrrole does not really abstract any proton. It's a very, very weak base, because before the reaction, this guy's aromatic. Once you add proton onto it, this guy becomes non-aromatic, not an anti-aromatic, because it's not doesn't have conjugated pi system anymore. This nitrogen becomes sp3, so it breaks the conjugation. Okay, all right, that's the reason why if you look at the what's called electron density map for pyridine, you're gonna see the red area right here. There's a high electron density. The lone pair is localized right here. Okay, in contrast to the lone pair of the nitrogen, this lone pair is delocalized in the ring. That is not free. This area doesn't really have a lot of lone pair. You can see the blue-ish color. Not a lot of electron density on the nitrogen. Okay, and all right, yeah, these are all aromatic heterocycles. Heterocycles mean are cyclic compounds containing heteroatom. Pyridine, pyrrole, you just saw it. Furan, thiophene, pyrimidine, imidazole, purine. The last 3 you probably have seen in DNA structure. Okay, all right, we're gonna do this together. All right, I'll have you do it first, and we can check the answer together with me on the next video.